Okay, so hello everyone. Well, in this video, I wanted to make an exercise uh, related to how the power of an induction motor is analyzed. Okay, so remember that in a previous videos we analyzed this power flow and losses of an induction motor, and we discussed that, well, we can calculate the input electrical energy or electrical power that is introduced into the induction motor by taking the square root of 3 times the line voltage times the line current times the power factor, no? This cosine of theta basically refers to the phase angle difference between the voltage and the current, and this is essentially the power factor. And this input power, well, has some losses, no? First, we have the stator copper loss and also the core losses. So the input electrical power has the following two losses. So if we take the input electrical power minus the stator copper loss minus the core losses, you will obtain the air gap power, no? That is the power that is transmitted from the stator to the rotor of the induction motor. But also this power, no, this air gap power that is transmitted to the rotor has some losses, in particular rotor copper losses related to the electrical resistance of the rotor. So if we take the air gap power minus the rotor copper losses, you will obtain the converted power. And you can use this converted power to, for example, compute the induced torque, okay? Because based on this expression, we know that the converted power is equal to the induced torque times the speed of the rotor, okay? And well, this converted power has also some losses, in particular mechanical losses related to the friction and windages present in the motor, and also some miscellaneous losses. So we have the converted power, uh, well, has the following two losses. So the output power is essentially the converted power minus the friction and windages losses minus the miscellaneous losses. Okay? And based on this output power, we can compute the load torque, no, or the output torque provided by the induction motor. Okay? So we know that the output power is equal to the load torque or the output torque times the speed of the motor, no? Sorry, of the rotor. And based on this quantity, we can also compute the efficiency because we can compute the ratio between the output power divided by the input power. No? That is a measure of the efficiency of this induction motor. So the idea of this video is that we see how we can compute this output power based on the input power and also by considering all the losses that are present in the induction motor. So to this end, we can solve the following exercise in which we have the following data. We know that 480 volts, 60 hertz with a output power of 50 horsepower, three-phase induction motor is demanding 60 amperes of current at a 0.85 power factor lagging. We know that the stator copper losses are of 2 kilowatts and the rotor copper losses are of 700 watts. The friction and windages losses are of 600 watts and the core losses are of 1,800 watts and the strays losses are negligible. So based on this data, well, the stray losses, remember that are the miscellaneous losses, but we can consider them as negligible based on the information provided by the problem. So we need to compute the following quantities. First, the air gap power, the converted power, the output power, and also the efficiency of the motor. So let's solve this exercise. Just let me share my screen. I need to go to the file to my tablet. No? So if we go to my tablet, I will share the screen of my tablet. Just one moment. We'll have the following information. Okay. First, we know that we have here the input power, no? And I have write the input power here in this section of my tablet. We know that the input power based on the previous diagram is the square root of the line voltage times the line current times the power factor. No, remember that this is the power factor. And also I have write down in this section the data of the problem, no? The line voltage, the output power of the motor in horsepower, the frequency of the three-phase power supply, the line current, the power factor of the motor, and also the losses, no? The stator copper losses are these ones, the rotor copper losses, the frictions and windages losses, and also the core losses. And well, if in this section also I have draw like a simplified version of the power losses diagram, okay, that we discussed previously. So the first aspect that we want to solve is to compute the air gap power. So we know that the air gap power, no, the air gap power is equal to the input power, no, the input electrical power minus the stator copper losses minus the core losses. Okay. So based on this data, we know that, well, we have the input power that is this expression, no? So we can say that the air gap power is equal to the square root of the line voltage times the line current times the power factor, okay? Minus the stator copper losses minus the core losses, okay? And well, we can substitute information that we have related to the data of the problem. So we can say that the air gap power is equal to the square root of 3 times the line voltage, that is 480 volts, times the line current, that is 60 amperes according to the problem. And also we know that the power factor is 0.85, okay? Minus the stator copper loss. And according to the data, we know that the stator copper loss is 2 kilowatts minus the core losses that are 1,800 watts. Okay, so this is the information of the problem. So we compute all of this, we will obtain the following, that the air gap power is equal to 38,600.64 watts. Okay, that is the air gap power. And also based on this data, well, we need to follow the power flow diagram, no? We know that, well, the second point is to compute the the converted power, no? That is this P comp. But we know that according to this flow diagram, that the converted power is equal to the air gap power minus the copper loss. Okay, so the converted power is equal to the air gap power minus the rotor copper losses. So we can say that the air gap power, sorry, the converted power is 38,600 point 604 watts minus the rotor copper losses that according to the problem are 700 watts. And this is equal to 37 900.64 watts. Okay, now this is a 7. So this is the converted power. And also the problem is asking us to compute the output power. So according to this flow diagram, we know that the converted power is equal to, well, the converted power has the following losses. We have the friction and windages losses and the miscellaneous losses. But well, according to the data of the problem, we know that the miscellaneous losses are zero, okay? Or they can be eliminated from the analysis. So based on this flow diagram, we can say that the output power is equal to the converted power minus the friction and windages losses. So the converted power, according to the previous result, was 37,900.604 watts minus the friction and windages losses, that is 600 watts. And this is equal to 37,300.604 watts. Now, this is the output power. And we can compute the efficiency in percentage. We can say that the efficiency is basically the the output power. Let me erase this, no? This is equal to the output power divided by the input power. So we can say that the output power is this value, no? 3,300.604 watts divided by the input power. And the input power is this expression, no? That is the square root of 3 times the line voltage times the line current times the power factor, that is 0.85. And this is equal to 87.9718%. No, this is the efficiency of this motor, okay? That so based on this information, well, I forgot to place here the percentage, okay? I need to be completely clear about this result. And well, we can use this information to know the efficiency, no? But you need to analyze this power flow diagram. Now, let me go to this section again. Okay, let me go to this section. That is in this part, okay? Okay, so based on this circuit, we can know what is the stator copper loss, no?